All right, good afternoon. This is Scott Dahman of PowerWorld Corporation, and I'd like to thank everybody for joining today. Today, Professor Tom Overby is going to talk about some new features that are really extensions to the weather features in PowerWorld Simulator. These are features that are new and will be available in the upcoming version 24. Professor Overby was actually one of the original founders of PowerWorld Corporation and the developer and architect of the original version of PowerWorld Simulator, even before it was commercialized, and is still involved today in the development. He's currently a professor and holder of the O'Donnell Foundation Chair 3 at the Department of Electrical and Computer Engineering at Texas A&M University. He's also a key part of the leadership at the Smart Grid Center at Texas A&M University. And if you've never been there, it's worth the visit to College Station just to see the Smart Grid Center. Pretty impressive. So prior to joining Texas A&M University, he was on the faculty at the University of Illinois at Urbana-Champaign. And not coincidentally, PowerWorld Corporation is headquartered in Champaign, Illinois, and most of our staff still works here, although some of them are remote and work in different locations around the U.S. Professor Overby is a native of Wisconsin, and he received all of his engineering degrees, bachelor's, master's, and PhD from the University of Wisconsin at Madison, and also has some experience working at Madison Gas and Electric prior to his academic career. So with that, I'll turn it over to Tom. Oh, and one other thing I'll mention too, before Tom gets started, this presentation is actually kind of builds on an earlier one that he gave in February that talks about kind of the basics in the first implementation of our weather features. If you haven't seen that, I'll put a link to that in the chat, a link to that page. And the same page also has a place where you can download today's presentation as well. And we're recording this. When it's complete, we will edit it and process it and also upload it to the same web page. So you'll be able to view that later. Okay, with that, I'll turn it over to Tom.
Okay, thanks, Scott. As Scott said, this is going to be a webinar about some of the weather stuff that is in PowerWorld Simulator. Some of it is in the current version of Simulator, which is version 23, and then some of it is coming out in version 24 that's due to be released in about October. PowerWorld will make a beta of 24 available. So if you're interested in that, which would have the features that I'm talking about here today, just send Scott an email at the address given here. And as Scott mentioned, this presentation will be available afterwards, so you can get emails and stuff from there. Scott did a nice job of covering my bio already, so I won't say much more about that, other than I have been involved in PowerWorld since its starting in 1996, and I continue to do some code development. I have been active in doing some of the weather development. Okay, Scott mentioned our facility that we have at Texas A&M, and we would invite everyone to come visit our facility. We would particularly invite you, if you're interested in short courses, to come to our short courses. We've got 3 of them coming up this fall. Actually, I typed the wrong. I typed one of those. The planner on the planning and operation of large-scale electric grids is correct. That's for non-technical people. The second one is a planning course, and the title's a little bit wrong there. But if you go out to the website, you'll see the right title. Then we have a GMD course coming up in October. Great facility there. If you want to see the great facility up in Champaign, PowerWorld has some training coming up at their facility there. One is in September. Actually, 2 are in September, and then 2 are in November. So either of these are great opportunities if you want to learn more. Okay, so with PowerWorld and weather, we've been working on this for more than 2 years now, and PowerWorld Simulators as a result has gained a lot of weather modeling capability, and it is continuing to gain more. The way PowerWorld does development is once a version is released, there's often continual development on that version. So once version 24 comes out, that doesn't mean we're going to stop adding additional functionality to weather in version 24. So we are continuing to move forward with this. Currently in Simulator, you can load quite a bit of weather information. There's different ways to do it. There's a PWW format, which I'll talk about. You can load aux files. That is an okay way to do it, but with weather, the problem you have with aux files is there's just often so many records. CSV files are an older approach, so we don't use that too much anymore since the PWW one is so much better. What I will show in this presentation is we do have weather data going back to 1940 that is available, and you can pretty much use it in PowerWorld right away. We also deal with forecasted data, and forecast data is available as well, and that's updated every 6 hours, and it goes out about 16 days. I will talk more about this modeling approach that PowerWorld uses, which is called the PFW, which stands for Power Flow Weather or Power Flow whatever models, which are a way that we map weather information into actually affecting the power system objects, with one example being changing the max megawatt on a wind turbine generator based on the wind speed. Okay, when you work with PowerWorld Simulator, particularly with the newer functionality, like with what we're doing in weather, it does help to know both what version you have, but also what build date of that version you have. If you have Simulator, you can easily see this by selecting Window About, and it shows a little dialog there that says what sort of add-ons you have. It tells you the version that you have. For example, here in the slide, I've got version 24 beta, and then it tells the build date. And some of the weather features, as they get developed, will be available with particular build dates. So that can be helpful in knowing exactly what you have. And if you have questions about what you have, and you send an email to PowerWorld, it helps if you let people know your build date. Okay, so why are we doing this? Why we're doing this is the electric grid depends on weather, and it always has in essence. But more and more it depends on weather, particularly as we add more wind and solar, and we try to operate the grid closer to its limits, and we have a grid that is so dependent on weather, to some extent the wind's blowing or the sun's shining, and we have now potentially weather-dependent transmission line limits. That has been the case for a while, and actually I've worked with weather in the power grid pretty much my entire career, going back to when I was an undergrad doing my senior design project on bringing weather into the Madison Gas and Electric Control Room. But it certainly has gotten more important over the last couple of years, and I think it needs to be added into the planning, and that's what we're trying to do here. In doing this, it is important to kind of manage accuracy expectations. One of my more favorite technical quotes comes from George Box, who was a professor at my alma mater, University of Wisconsin-Madison. He actually formed the statistics department there in 1960. One of his quotes is, "Remember that all models are wrong. The practical question is how wrong do they have to be to not be useful?" And then a second quote, actually from his same 1987 book, is, "Essentially all models are wrong, but some are useful. However, the approximate nature of the model must always be borne in mind." Certainly, this is something that when we do power system analysis, we have to always keep in mind. For example, the common power flow that we use is usually a positive sequence one, so that has certain assumptions associated with it. We make assumptions on how the resistance of the transmission lines changes with temperatures. Often that assumption is it doesn't. Likewise, when we use weather information, we're going to have to make assumptions on how much accuracy and precision do we need in them. And that always depends on your application. And I'll talk some about that going forward. Okay, so this talk is mostly on weather, but we also cover other resiliency events, and those other resiliency events could be earthquakes, wildfire. I'm not really going to talk too much about geomagnetic disturbances, but PowerWorld does handle that. Potentially volcanic events and maybe eclipses. Collectively, I'm going to refer to these as ENIs, environmental inputs, but most of the focus here is on weather, and particularly it's weather in power system planning. Of course, the planning timescale can go from near real time out decades, and what weather is appropriate, of course, is application dependent. In using weather in power planning, you really have to deal with a couple different things. One is you need to have geographic information on your electric grid. It's hard to apply weather to the electric grid if you don't know where your electric grid is. Luckily, over the last couple of years, more and more geographic information is becoming available. Now it's pretty reasonable to assume that with the North American power grid, you have geographic information for the substations, and usually you'll have substations mapped into, or buses mapped into substations. This is something PowerWorld has done for a long time, at least 15 years. But increasingly, it's being populated in the regular models as well. So kind of the assumption on what we're doing here is you've got geographic information. But even if you don't, there's actually quite a bit of weather that you can at least see in PowerWorld. We also have large-scale synthetic grids, if you're coming at this from an academic perspective, that are geomapped, so you can immediately apply weather to them. Once you have the mapping, at least the geographic location, you need to have access to environmental inputs, for example, the weather information. What I'll show you here is there's a lot of information available in a public sense, and we try to make that readily available. The third part then is you have to have models that represent the impact of the environmental inputs on your electric grid components. And we'll talk about that as the presentation goes on. Just something that is kind of recent in simulator version 24 that I wanted to let people know about is in doing this weather analysis, a lot of times we'll be wanting to know where a device is located geographically, or actually sometimes we want to know where a weather station is located at geographically. And we would be manually typing in the latitude and longitudes into applications like Google Maps. And we thought, can't we just get simulator to do this? So the result is, yes, we do have simulator set up now that it can actually display in a web browser a location of a device, and we just added that to the right-click menu for buses, generators, substations, areas, pretty much any power system component. So you just right-click on geographic views, and now you can immediately see that view in Google Maps or Bing Maps or Open Infrastructure. So this is just kind of a convenient tool, but actually something that I use a lot now. Just the image on the bottom right is one that we made up that shows once you have geographic information, you can do all sorts of interesting visualizations. That's a visualization of an electric grid model that we were doing for a project for Southwest Power Pool, where we were looking at joining the east and the west grids, AC, and we had everything geomapped. So I was like, oh, to get a feel for the load distribution, why don't we just contour it? And that's what the image shows. If you look at it there, Texas looks mostly black, and that's because we were not including ERCOT in this analysis. So we weren't, of course, deliberately excluding Texas from the image. We just didn't have it in the model. Okay, so in doing weather analysis, you know, your starting point is saying what weather information do you have available? As we've been working with utilities on this, and in some cases, the weather information that they're most concerned about is from a particular location where they are measuring weather, perhaps continuously, and they wanted us to model that particular location. So we have set it up so that if you have a weather measuring device at a particular location, we can handle that. But then as we got into this, we realized that we should be tying into all the other weather data sets that are available, and I'll be covering a lot of that as the presentation goes on. I should say a really good, useful link if you're interested in weather data sets and power system planning is what I've shown there in the second bullet. That's a report from the Energy Systems Integration Group that came out in October of 2023. And I would highly recommend reading it. It's a free download if you're interested. This is a table that I got from that report on the right that shows some of the weather modeling input sources that can be used, and then it shows their relative benefits in terms of things like spatial resolution, time resolution, and things like that. In this presentation, I'll mostly be talking about the second and the third line, the ERA5 and the HER data, which together give us really good coverage on the weather. I've got some quotes over there on the left from that report. The gist of it is that we need weather in planning. That's what the first bullet is showing. And then the second bullet is showing that, you know, it's not trivial to put weather into planning and to put it into planning software. And having worked on this for a couple of years, I can definitely agree with that report. It's not a trivial undertaking, but it is manageable. And it's something that I think we really need. And PowerWorld is quite a ways down the road on doing this, but it's also, it's going to be, you know, it's not a 2-year road. It'll be longer, but we've made quite a bit of progress in these 2 years, and particularly over the last year. Here's a paper that was accepted for the 59th Hawaii International Conference on System Sciences that kind of talks about this modeling methodology. The way Hicks does paper reviews is that it's a double-blind review system. So this paper has been conditionally accepted, but it hasn't been finally accepted. So I can't really reveal who the authors are on the paper, but the papers are due in about a week. So once it gets finally accepted, we'll post it up on the website I mentioned there, and you can get access to it. Okay, with respect to weather, PowerWorld's goal is to make this as easy as possible for power system engineers. The idea is that we're dealing with a power system engineering community, not a weather modeling community. So we want to make it as easy as possible and still give you a lot of functionality. So we're working in a couple of different ways to do that. One is we have a format that's actually a public format. It's PWW files. It's a binary format, which allows for pretty good file size that allows us to store weather information and potentially other environmental inputs and give the software, PowerWorld, or actually other software packages could use it, ready access to it, because some of our customers said we want to have weather stations that are at particular substations. You don't need to have your weather stations on a uniform grid to use this format, and that's how it's different from some other formats that we'll talk about. Okay, One of the other formats that is very common when you get into weather modeling is called GRIB, or the GRIB was the first version, and GRIB 2 is the second version. That stands for gridded binary or general regularly distributed information in binary form. It's a very common format for the exchange of weather model information. The World Meteorological Organization standardized GRIB in 1994 and GRIB 2 in 2003, although GRIB 2 does continually get updated. Both the GRIB and the GRIB 2 are widely available formats. So weather models are often put out in this format. And we're going to set up Simulator in version 24 so it can directly load GRIB files, which I think will give people pretty convenient access to a lot of data. There are some general repositories, like for some of the data sets. University of Utah has one where there's a lot of data available. So I think this will be very helpful. One of the data sets we've been using a lot over the last year and a half is called ERA 5. The 5 comes from it being a fifth generation reanalysis of global climate and weather since 1940. If you get ERA 5 data, which we have available in the PWW format, what you're getting is over a desired footprint. And for us, we use a footprint of mostly North America, excepting Alaska and some of northern Canada. It uses a 0.25 degree grid, and it includes fields like wind at the surface, wind at 100 meters, some solar values. It's got wind gusts in it. It's got temperature and dew point. It's a very good format to use. The only issue with ERA 5 is because it's got a 0.25 degree resolution, which is about 30 kilometers. In some situations, it's not going to give you enough resolution. But in a lot of planning situations, ERA 5 is probably going to be fine. Another format that we actually heard about because of the feedback that was given to us on an earlier presentation that I gave. And I should say that I have greatly appreciated all the feedback that people have been providing us on this. It is very helpful, and we very much welcome your input. So please continue to provide us input on how we can improve this. The second data set is called HER, or H, I guess it's HRRR. High resolution rapid refresh models, which are provided in the US. Well, they're provided by NOAA in the US. This is a 3-kilometer resolution, hourly updated assimilation modeling system. The picture there is the full data set of HER. If you actually deal with all the elements in this, it's actually 1.9 million elements that you're dealing with. So it gives pretty good resolution. If you look at that image there and you think, why is it on kind of a curved shape? It's because it does not use the same projection system that the ERA 5 uses. Rather, HER uses what's called the Lambert conformal projection, which is a conic projection, which is a little bit trickier to map into latitudes and longitudes, but its advantage is it's a uniform spacing of 3 kilometers, and it covers Canis. There's another one that I believe that covers Alaska, but we haven't been dealing with that one yet. To make it easy to get access to the ERA 5 data, what we have been doing here at Texas A&M is we are posting them on a website. It's given their electricgrids.enjr.tamu.edu/weather data, and we update these pretty much daily. And we have, data going back to 1940 that covers the shaded region there. The footprint that we're covering has about 38,500 data points, so it's quite a bit less than the HER. But still, you know, when you go back to 1940, the amount of data adds up. It's total about 250 gigabytes. But having said that, it's not that much data. You know, you can go out and get a external hard drive that stores much more than 250 gigabytes. I've got one here that stores something like 10 terabytes. So once you get this data, you have it, and then you just have to keep updating it if you want to have the latest. This is a website where we have it available there. When I go out and get it, which I of course have gotten, so I don't have to download it very often. The historical data we pack it by decade, and then we zip it. And it took me on my computer about 4 minutes to download each decade. So it's a bit of time, but once you have it, then you have it. Okay, so once you have this data in simulator, the key place to go is on the simulator ribbon. You go to tools, and there's a one called weather, and then there's a display called weather models and information, and that has a number of different pages associated with it. One page is a weather stations page, and that allows you to view the weather at any particular time that you want, provided you have the associated PWW file. And I just showed you how you can get access to that. We haven't made her files available in PWW format, but we probably will soon. Once you go to this page and you've downloaded the data, then all you have to do is just click on just get weather for desired date, and it will bring in the weather for the desired date into simulator, whether it's ERA 5 data, which is what I'm showing here, or the HER data. This slide here shows an example of the HER data. PowerWorld's string grids, the kind of the case info displays, they can actually display quite a few rows of data, and they can actually display quite a few columns of data. I just loaded up some recent HER data and scrolled through it, and it's got 1.9 million weather stations in it. And it scrolls through pretty fast. Once you have it in there, you can plot it. And there's an example of a plot of the wind speed at a particular location. Or we've got histogram capability now. So if you want to make a histogram, it's really easy to make a histogram. So I made a histogram of the wind speed at a particular location there. In doing this weather modeling, we realized that simulator needed to have a consistent way to, well, it needed date time values. And in general, PowerFlow cases do not need to have an associated date and time. And you know, if you study a peak 2028 model, it really doesn't matter what particular day or time you're studying. So you don't need that, but sometimes it's helpful. So in simulator now, if you go out to case information, case description, you can actually enter a case date, which is the date associated with that case. Maybe it's an EMS model, and that's the associated date and time that it's from. Maybe it's a future model, and you know, you just want to give a general feel for when it is. We also have a separate date and time for the weather, and you can just enter, well, the weather is usually auto set when you load the weather data. Weather can be shown either using the local time zone, or it can be shown in the UTC format. UTC is just the coordinated universal time. The advantage of that is it doesn't depend upon time zone. Also, when we show data, we can show dates and time. We can either show it in the traditional way of month, day, year, or we can show it in the international standard ISO 8601 format, which is year, a month, day, then a T, and then the time associated with it. I've been using the term weather station. I did just want to say what I mean by weather station. PowerWorld uses the terminology weather station just to refer to an object that stores weather data. A weather station object must have a latitude and longitude. Usually they have an elevation associated with them, and sometimes they can have other identifiers. The weather station might be an actual location. It could be a airport location. It could be a weather station that you have at a substation. But it also might be just a point from a weather model, like ERA 5, the weather stations, the data points are on a 0.25 degree grid. HER uses a different grid with 3 kilometer spacing. So there's not really a station there. It's just a model point, but we use the terminology weather station. Once you have weather, you can show it in your PowerFlow case, even if you don't have geographic coordinates in the case. You just can't, of course, apply it to the case. Like most objects, weather can be saved in an aux file. So if I just want to save weather for a particular location or not a location, but at a particular time, oftentimes I'll store it in an aux file. The advantage of aux files is you can go in and you can edit them. The disadvantage of aux files is they're not designed for loading millions of records in. They can load hundreds of thousands of records pretty well, but once you start going into the millions, it becomes a problem. As we're showing weather, a lot of times we'll want to find weather for a particular geographic location. So we added a button on this page. It's the same weather page I mentioned earlier, where you can find a desired location. And here I typed in the location for College Station. Once you have weather data, you can visualize it, and PowerWorld has support in the contouring for visualizing the weather. There's actually a couple ways to visualize weather. One way is to use this object that we introduced maybe in version 22, I think, called the spatial data object, which does not require objects to actually be on a one line. We added this for showing the electric fields associated with, say, a GMD. But you can also use it for weather. You just select spatial data and then the weather type that you're interested in, and do your contour kind of as normal. In doing contours, we did add a feature that allows the contours to be removed from the background. Like people were saying, how come my contour is going out into the ocean? Which did not make sense for power system data. So we have an option to not show contours on the background, or we have an option where you can not show it on the borders as well. With weather, sometimes you want to show it on the background because you might want to see what's going on offshore. So now we have two options to decide whether you want to show contours in the background, which would often be the ocean. Now there's an example contour of 100-meter wind data that I made using ERA 5 data. I know it's ERA 5 because the weather station count there is 23,000. What I did is I took the North American data, which had about 38,000 weather stations in it, and then I reduced it down to just the lower 48, what we call CONUS, including, of course, DC. And that's a visualization of the weather in CONUS. One of the new features we added that is now available on any contour, but we added it initially for the spatial data contours, is the ability to put data symbols on the contour that show the contour value at the particular location. We made it very easy to put these on and very easy to customize them and very easy to get rid of them. So if you want to see a visualization of say the wind speed where you see little values showing you the actual speed at the location, that's an example. You can add as a suffix the units to this, but that gets to have, like in this case, I'm showing miles per hour. There'd be a lot of miles per hour on there, which just isn't needed if you already know what it is. These are the available AR5 fields in simulator. We did just add the wind gusts. We haven't updated the files out on the website yet for the wind gusts, but we'll probably be updating them in the next couple weeks. We had 8 fields, now we've got 9 fields, including the wind gusts. With the HER data, we're figuring out what we want on this. And we would really value your feedback on what we should be having on this. We have the temperature, dew point, wind speed at the surface, wind speed. HER gives you the wind speed at 80 meters, which we convert up to 100 meters. There's some solar information, wind gusts. We've got hourly precipitation, percent frozen, and we also added smoke. Okay, and you can also show derived values like humidity. Okay, so in doing weather modeling, of course, the idea isn't to just show the weather. There are many other programs that show the weather, but it's to relate the weather to the power system models. And that's where we've introduced this concept of a PFW model. The PFW models, power flow, whatever models, or power flow, they started out power flow weather, and now they're power flow whatever. We actually leveraged the code that we had developed for modeling the stability devices like a machine model, an exciter, a governor, and said, hey, we can apply this same concept in the power flow and just have inputs being the weather. So we are using that same concept. So it's actually very similar to what we do in stability. This is an example of a weather model, that a PFW model that we set up. It was the default wind speed models where it takes a weather input and maps it to a power system value. In this case, the map value is the normalized output of a wind turbine generator. And with this, if the wind's blowing at a particular speed and you have a particular type of PFW model, then you know what the output of your wind turbine should be scaled to, and that is how we scale these values. We can develop these PFW models pretty fast. We've got a general PFW model that is kind of a user-defined wind power curve, or speed power curve for a wind turbine. And I'll show you how you can get a lot of data with these curves in just a second. There's other types of models that we are working on developing. Of course, ambient adjusted line ratings, dynamic line ratings. The ambient adjusted one might just take temperature at a particular location, or maybe you can take it at more than one location. If you want to go dynamic line ratings, maybe you want to add in wind data and other data there. We might go and do stochastic models, like we've been playing around with how does the grid respond to earthquakes. So we take asset fragility curve, which is a probability of failure for a particular earthquake parameter. Here we're looking at peak ground acceleration, or PGA, and then it tells us the likelihood of that asset failing. This is just an example of the standard generator dialog that if you use simulator, you know about the generator dialog. Over on the right, there's a page called the PFW models and weather page, and that's where you can, if you like to manually enter data, you can manually enter data there. But of course, we also have lots of ways that you can automatically enter data. This is an example where when we set up some of these models, we often are dealing with entering a large number of PFW models at once. A lot of times we're just using default parameters, so there's a way to pretty easily put in the default parameters there. One way that we wanted to make it easy for people to get started with this is because in the US, the EIA puts out the EIA 860 data sets, which tells us a lot of information about all the generators. We actually set up a power system grid that we call a copper plate power flow model because it doesn't have a transmission grid in it, but it has all the generator models in it. And then we can visualize and manipulate this grid kind of like just any other power flow model. If you're interested in the details of that, it's given in the publications below there. Of course, this is a copper plate model, which means there's no transmission grid. So it's just a way to visualize the weather impacts on generators, for example. This is an example where I just am showing you the weather data that we have that is set up as PFW models. This is coming out of the EIA 860 case, and we've got these cases up on the Texas A&M website as well. On those cases, we are not, of course, using the CEII bus numbers. We're just using the public EIA 860 models, but we do have mappings available that relate most of the EIA 860 generator numbers to the associated CEII ones. Of course, we can't make that generally available. One of the challenges we had in doing this work was we did not have access to actual wind turbine power curves. You can buy this data, and some people will buy the power curves for particular wind turbines. What we were happy to find is that there is actually a data set, and I've listed it there. It was put out by PNNL, and it provides access to the power curves for all the wind turbines in CONUS as of the end of 2020. And they have a power speed curve. And what we did is we set up simulators so you can just paste in their power speed curve into our general model. So now for all the wind turbines up to the end of 2020, we have the actual wind turbine power curves available. And that's just a public website there, so it's public information. So we're quite happy to get this. This is just kind of a step-by-step into how I took that Excel spreadsheet. And if you want that Excel spreadsheet that you can paste into Simulator, I can just email it to you. But we also, I think we have this data actually in our newer EIA 860 models that we're posting online, but it's very simple to do. I just loaded it into Excel, I copied it, and then I directly pasted it into Simulator, and Simulator knows how to interpret that field from the Excel spreadsheet. So then you have it. This is something that you just have to do once, and then you're done. This is an example where I set up we took the EIA 860 data set that we had. This is wind and solar installed at the end of first quarter 2024. And then we started applying weather to it. In doing that, of course, we have to map the weather we have to the different power system elements. For example, the wind turbine generators. There's no particular best way to do this if you don't have a weather measurement right at the location. But there are some good data interpolation methods that you can use. Some are grid-based, some are closest neighbors, some are delineate triangulation. When you use the HERD data, the good thing is because it's 3-kilometer resolution, you're going to have a measurement within 1.5 kilometers of your device. And of course, with a wind farm, that device is often spread over a pretty large area. You still have to deal with local terrain, and we certainly recognize that if the goal is to find the output of a particular wind farm at a particular time, like real time, it's a challenging problem because wind can vary quite a bit locally. I've got a picture here from the earlier publication, the ESIG publication that I mentioned, and it says the impact of spatial resolution on estimating wind. This is the image on the top is kind of in the Portland or the Washington State, Oregon area, kind of showing the Columbia River Gorge and Mount Hood. Clearly, the wind varies quite a bit in that location, and you get things like a wake coming off of the mountain. Era 5's not going to cut it in a location like that. So I did take our herd data that we have, and I visualized it. This is Washington State on the top and Oregon on the bottom, and the Columbia River going in the middle there. That's a contour that I created in Simulator, just loading in one of our herd data sets and showing the 100-meter wind. And you can, I was using a nearest neighbor contour algorithm there, so you can kind of see the 3-kilometer resolution. Is that perfect? It's like, no, that's not perfect, but it's got pretty good resolution associated with it. So how much resolution you need, of course, that's application dependent. In doing this analysis, what we are doing in the testing of it is we tend to test with the full data set. For Era 5, it would be, the North America footprint that I showed you. For the her stuff, it's the full nearly 2 million weather station set. We hope you don't do that, and most people won't need to do that because you're probably just concerned about the weather in your location. Maybe not your particular utility, but it's a much smaller footprint than what we're testing with. So we have a tool that makes it pretty easy to reduce these data sets down. I would encourage people, if you get like our North American data set, to reduce it down to make access to everything much faster. I reduced the North American one down to CONUS for some of our work. We've also set up some that just cover the state of Texas. And it's something that you just kind of have to do once with the historical data and then just keep up to date with the newer data. Applying the weather can be applied in PowerWorld in a number of different ways. You can look at it at a specific point in time. You can get a summary of a large amount of weather at a single location, or you can do time series analysis. I wish I had time to go through all these techniques in detail because they can be pretty powerful techniques. But I wanted to make sure that people could at least see how to apply it at a particular point in time. If you get the PWW files and you go out in Simulator to the weather stations page that I've mentioned, you just, in the middle there, it asks you what date do you want to look at, date and time. You want to express it in UTC or local time. Then you can either just get the weather for the desired date, and that doesn't apply it to the power system, or you can apply it to the power system. And once you've done that, it's adjusted the outputs, max megawatt values of wind turbines and solar based on your PFW models. And then you can just solve a power flow or contingency analysis, whatever you want to do with it. And then you need to restore the values at the end. So this is an example. I just took an example point in time. As someone who grew up in Wisconsin, I remember Christmas Eve 1993 as being a very cold day. So I thought, I wonder what the winds look like on Christmas Eve of 1993. So I went out and quickly generated this display. This is a visualization where the greens show the wind turbine outputs at that particular point in time. And I created this contour just by applying it to the power system and then creating the contour. In doing this weather analysis, of course, people often want to find these unusual weather times. So we set up a page. It's on the same weather-related models and information display. It's just a couple pages over from the weather stations one. It's called Find Outliers. This allows you to search through a data set pretty quickly and find particular outlier values. In this example, I was looking at a particular geographic footprint, Texas, and I looked at the entire data set range, 1940 to 2023, and I said, what are the days? Actually, it's just looking at a particular hour in each day. In this case, I was looking at 6 p.m. local time. What is the time, or what days had the lowest temperature at that time, conditioned on the wind speed over the footprint being less than 10 miles per hour? And then you just click find time points, and it tells you the time points there. For example, one was in 1989. Also, it looks like it was around Christmas time, this December 23rd. A couple ones from 1947, one from 1951, a couple from 2011. And once you've found these, you can store them in a PWW file. You just toggle the selected and save them in a PWW file. Then you can do later analysis on it, or you can actually just apply it right on from this form. We have a number of different ways that you can simulate lots of weather information. PowerWorld has a tool that we actually started developing for TVA back in about more than 20 years ago that allows the analysis of sequential time points. It's called the time step simulation. It's been augmented quite a bit over the last couple of years, and it can handle a lot of weather values, and it allows you to rapidly process a lot of weather. Here I loaded up my 1940 file and looked at the weather for 1940 over the entire footprint. I just picked a particular location to focus in on, Seattle here. There's the weather data associated with Seattle. Using the time step simulation, I could not only visualize this weather data, which I'm doing here, but I could also solve power flows using that weather data and look at the impact on the grid. Of course, you're probably not going to want to just solve arbitrary years. Rather, what you're probably going to want to do is find those outlier conditions and solve them, but we certainly make it easy to do both. In presenting this, people will often say how to get access to real-time data and how to get access to forecasted data. There are a number of ways to get access to it. We actually are downloading automatically the NOAA, the NCP forecasts, which are on a 0.25 degree. They go out 16 days, and we make those available in the PWW format. We actually hope to get access to longer-term formats or longer-term forecasts as well, or maybe do some working with some of our partners here at Texas A&M in the Atmospheric Sciences Department, longer-term climate simulations. As has been in PowerWorld for a couple of years, you can go out and get the current forecasted data on a station-by-station basis. Other sources like the HERD data are probably much better, but this is still available if you want to do it. And there's actually on the weather stations page, there's a tool there that lets you download this the MEDAR data very quickly and then load it into simulator and use it just like before. Going forward, we are working on developing a lot of additional models. And again, these models don't take too much time to put in. The challenge in making up PFW models isn't in necessarily coding them. It's more in figuring out how are you going to model things. And there we certainly appreciate the feedback we've already gotten from people out in industry, and we look forward to getting more feedback. Lots of future directions to pursue. We are continuing to work on this. We need more PFW models. We need the integration of weather into tools. Like I'm thinking contingency analysis could be extended where the contingency is looking at a particular point in time from a weather perspective. So you apply weather and you look at perhaps an incremental change in load based on a change in the temperature and dew point, and then you might change your solar and your wind based upon what the weather is showing. as I mentioned, support for other weather types, more detail, higher resolution data sets are available, and we're trying to figure out which fields out of herd do we want to make available, more validation, lots of stuff going on, but I think we've made good progress. So I would welcome any questions that people have. You can certainly email me at either of those emails. Again, if you're interested in getting the version 24 beta, email Scott at powerworld.com. Thanks.